Welcome to the webinar today. Matt, our CFD application engineer, and myself have worked on several different external aerodynamic CFD projects in the past couple of years, and we worked together in order to condense and sanitize some of the key lessons learned from those experiences, and we wanted to share them with you today. And the title of our webinar is Low Subsonic Aerodynamic CFD Validation using Simcenter STAR-CCM+. Brief overview of what we're going to talk about today. First, I'm going to give a company background and then discuss a high-level executive summary about the case study we're going to examine in detail. And then I'm going to hand the reins off to Matt, who is going to walk us through the aerodynamic design process with and without CFD. He is going to tell us why CFD validation is critical, and going to end with the problem setup for our case study, and then discuss some of the key takeaways. And then we can take questions at the end. So there's two parts of the company. First part is focused on software sales, and we sell software on behalf of Siemens and support it. And our specialty is simulation, design, and PLM software. A couple of the products that we support are listed on the screen. And the second half is focused on engineering services with a specialty in structural analysis, design, as well as CFD consulting for primarily the aerospace industry, but also others. And if you have any questions on these items, we're happy to talk to you. Okay, now diving in. So at a high level, companies face shorter time to market cycles, increased product complexity, and cost pressure, just to name a few pain points. These business forces drive the need for advanced design methods so products can be developed faster, at minimal cost, and with a customer-centric approach. One of these advanced methods is Simcenter STAR-CCM+, which is an advanced multi-physics CFD simulation tool that can be leveraged for external aerodynamic analysis in the aerospace industry, as well as many other fields and applications. If there's one idea that I'd like you to take away from today, it's this: integrating CFD into your product development, especially during the conceptual phase, can significantly speed up your time to market, cut down on costs, and provide deeper insights into your product performance. Now, let's take a second to examine a couple different product development approaches. The first approach is focused on prototyping and physical testing only, and this method often identifies issues later in the development process, which, as a consequence, requires higher costs to change your design. The next approach, labeled traditional approach, integrates CFD into the detailed design phase. As you can see, the development phase is on the bottom axis and the number of problems is on the y-axis. And by integrating this advanced analysis method, it shifts the curve to the left, and it helps to uncover problems earlier, leading to cost and schedule savings. And the final approach I want to discuss is front-loading CFD into the conceptual phase. And this strategy detects issues very early, reducing the risk of rework and delays. Now, this is a high-level qualitative description of why incorporating CFD and advanced methods into your design process is critical for project success. But we need more than that. And that's why today we are going to discuss a specific case study using the NASA Cessna 210 measurements and OML to discuss this concept with respect to measurements and facts. So I am now going to hand the reins off to Matt, and he is going to walk through this case study.
Yeah, thank you, Ted. I'll take it from here. So let's talk about why we need to look at aerodynamic design specifically, because aerodynamic design can play a quite significant role in your design phase. And one of the key things is when we implement robust CFD practices, we can minimize the major design cycle. Where this cycle sits is actually within the workflow diagram for your aerodynamic design process. Right here, we're looking at the workflow diagram. This is a small part of the overall aerodynamic design process. We're going to look at this from top down, from the conceptual design all the way down to the wind tunnel. And we can see that highlighted blue here is the major design cycle. Is basically the design change required after testing. So ideally, you will want to minimize this major design cycle iteration, so you can help saving costs. Meanwhile, it's still in the detail phase or prototyping phase. Now, when you implement CFD, we can see it being categorized here in highlighted blue. It's also called the inner loop. And when we don't implement CFD, we're basically taking like half of this inner loop out of the design process. And in-depth problems are not really identified until like later on in the development cycles. In this case, that would be a wind tunnel testing case. And with CFD, you can actually detect the problem early on before the wind tunnel test. So you can bring a more refined or a product that is more iterated in your maybe CAE or CA or CAD tool. So to highlight the significance, we'll walk through both approach with CFD and without CFD in the next couple of slides. So first, let's talk about what happens when we don't adopt CFD. So without CFD, a lot of times your aerodynamic design relies on traditional design tools like XFOIL or AVL. And typically a designer will start from two-dimensional 2D airfoils with something like maybe XFOIL. And this program specifically designs and analyzes low subsonic airfoils using the panel method. Then likely you import the airfoil data into a three-dimensional 3D tool like AVL. And AVL is a program for analyzing aerodynamics and also flight dynamics for aircrafts. It features the extended vortex lattice method specifically, but it is also limited to small angle attack and side slips. So now just let's take a look at the outcome when CFD is not quite involved. So if your conceptual design tool or your traditional in-house tool indicates that your airfoil is sufficient for your engineering requirement, likely your engineer will just gonna move on with satisfaction. And the only chance you're able to evaluate the performance will be at the physical test. In this case, we're looking at the NASA wind tunnel data. And unfortunately, the odds are not on our side. We can see that XFOIL particularly here failed at capturing the trailing edge separation. We can see that the data is diverging. But on the bright side, we can see that XFOIL is actually very accurate in the low angle attack, the linear region. And now if we import the airfoil data at the low angle attack into AVL, we can also predict quite accurately at the low angle attack. But we shouldn't really push this to the far right where you have a high angle attack. Since this tool is not designed for high angle attack, and specifically the imported airfoil data is only confident at the low angle attack. So even though like these tools are amazing at the low angle attack, but this still doesn't really picture the whole story. So let's see if CFD can capture the big picture. So CFD actually offers accurate prediction for lift across your entire flight envelope, including your takeoff, climb, cruise. It can predict forces and moment accurately because it actually resolves the boundary layer. As you can see in the picture here, within the CFD, especially our simulation, the airfoil mesh near the wall is actually further refined. This helps targeting the refinement and resolving the boundary layer. And combining this with the Navier-Stokes solver and turbulence model, CFD can handle like quite complex flow characteristics like separations, as we can see in the bottom right. And of course, this carries over into 3D, and you can even like investigate the entire flow field and visualize how air move around your wing or aircraft with streamlines. So now let's take a look at how CFD actually makes a difference. So here we're revisiting the charts we just saw 2 slides ago, and we have already seen that XFOIL is over-predicting here, specifically at the maximum lift. So the question here is, can CFD assess the comprehensive aerodynamic performance? The answer is yes. So if we look at it closely, we can see that the blue line represents the CFD data and is accurately predicting the maximum lift, and it follows quite closely to the experimental data as well. And we can obviously do the same thing for 3D the aircraft validation. So also we have the previous data here, and you might wonder what happens if we extend the airfoil capability far beyond its limitation, right? Like let's push it to the far right. Since especially the AVL here has really good agreement at the low angle attack, well, let's see what happens. So AVL actually is unable to predict stall and maximum lift, and this could be very dangerous because of the software limitations. So can CFD really help with capturing this peak or this stall in the experimental data? Actually, CFD could, and here we can see that the maximum lift is actually really close to experimental data, and also it provides a conservative prediction on the stall. This is roughly like 1 degree of angle attack ahead of the experimental stall. But however, all these are actually only possible with validated CFD practices. So now let's talk about why we need to validate our CFD. So validation essentially allows us to gain confidence in CFD analysis and also be informed when we make engineering decisions. Not just that, validation also addresses the inherent CFD challenges. Like there's really no one-size-fits-all solution, and most use case are independent. You can't really use one validated CFD process for another. And even within external aerodynamics, there are different use cases like I'm showing you right here on the right-hand side. So for example, if you have a CFD process for your supersonic, it doesn't really carry over to rotorcraft aerodynamic. And even though it might sound tedious to do a lot of CFD simulation and validation for each use case, but it actually has tremendous value. Like you can standardize your CFD processes. So likely 2 CFD engineers or aerodynamic engineers would technically get the same result if they use the same process. This really leads to the consistent performance evaluation across maybe different programs, different groups, or even across different engineers, and this can minimize overheads. So to have confidence in our own internal validation, we specifically follow the NASA verification and validation recommendations whenever it is applicable. So for verification, we specifically look at the iterative convergence and mesh convergence. Starting from residual conversions, we make sure everything is level off, and we also apply this to engineering quantity. So for this case, we're specifically looking at lift coefficient. We also make sure that lift coefficient itself is also level off. And particularly for a mesh convergence study, we have 5 different mesh refinement levels, and we have predicted the asymptotic behavior at the finer mesh. And we can see in the graph that the finer mesh are well within 5% error bound. So we can conclude that mesh convergence was achieved with our processes. So we have confidence in the fineness of the mesh. And moving on to validation. as we already show you, we compare our CFD data to experimental data to make sure we find good agreement. And on top of that, we actually also examine our model uncertainties for different models like turbulence models, where we're looking at Spolaris Maris, SSTK Omega, and we look at different correction models like rotation correction, and rotation curvature corrections. And we also look at implementing transition models. And we simulate all these different models in various combinations to assess their effects on the end results. So that finished off our validation approach. Now we can talk more about the details of our CFD practices. So let's start with our computational domain. We uses a half symmetry hemispherical fluid domain to predict longitudinal performance for the aircraft. This saves a lot of computational time and resources. And of course, for lateral performance, we use a full spherical fluid domain to account for side slip. And for reference here, this domain is roughly 50 times the fuselage length. And if we look closely, we see that the half aircraft is sitting at the center of the fluid domain. And now we can move on to boundary conditions. We are reusing the views from the last slide to highlight the boundary conditions on the fluid domain. For the far view, which is the outer shell here, we have the free stream boundary condition. As we briefly mentioned, we are using the symmetry boundary condition, and it is located at the center plane, cutting across the aircraft and the hemisphere. And finally, the rest of the aircraft surfaces are just no slip boundary conditions. Moving on to mesh. Right here, I'm showing you guys the polygonal surface mesh for the half aircraft. One thing to highlight here is that the wing, as the main lifting surface, is strategically refined further to accurately predict lift. And if we look at the polyhedral volume mesh, we're looking at a two cross-section view of the volume mesh. One is vertical and the other one is horizontal. And the total cell count we used for this particular run was roughly 26 millions. And of course, if we do a full spherical volume mesh, that will be the double of that. So after we looked at the mesh, let's talk about the physics settings for this study. So we are using the compressible flow solver with the ideal gas assumption. For turbulence model, it is determined based on the model uncertainty analysis. It turns out for our case that SARC QCR was the best performing one. And essentially this combination stands for, it was using the Spolaris Maris. It was using the rotation curvature correction RC, and it was also using the quadratic constitutive relation QCR. And at the boundary layer, we used the all Y plus wall treatment approach, but we also have it with a low target Y plus. So this approach basically resolves the boundary layer profile instead of modeling it. So after we solve the simulation, it is also quite important to visualize and gain engineering insight from the simulation. There are many ways to do so. I'll just demonstrate a couple ways that we prefer. Here, we're looking at the wall Y plus and the pressure coefficient contour on the aircraft surfaces. Note that these are actually plotted on the same half of the aircraft, but the pressure coefficient contour is just mirrored at the center plane. And similarly, we can look at the skin friction coefficient and the constrained streamline to identify separations. And on the right side of this image, we can see that there are local velocity contours being plotted at different sections of the wing. Hence, we can kind of grasp how like the velocity magnitude is changing across the wing and changing along the wing as well. So we are almost at the end of the presentation. So I'd like to summarize some key takeaways for today's presentation. Like Ted has mentioned before, if there's only one message you take away from this presentation is that incorporating CFD into your product development can always accelerate time to market, and you can mitigate a lot of costs and also you can increase or iterate your product further before you even reach the prototyping phase. And on the other side, CFD definitely shows a lot of capability in predicting lift and aerodynamic performances across the entire flight envelope. And CFD validation is actually really critical to allow us as a CFD engineer to have confidence in our decision making and also guarantee a consistent performance evaluation. So right now, I just want to take some time to talk about our future plans for webinars. So we're not just going to stop at low subsonic. So we will, in the future, we'll probably look at different other validation case. We will go through like a high lift, supersonic, transonic. There's already a lot of materials you can look into those, like in AIAA or NASA. One thing really interesting is we are currently looking into a 2D airfoil optimization with some of the other Siemens tool like HEEDs. And going outside of the aerospace industry, we also are doing a lot of marine applications, validating that. We also look into multi-phase flow. And the last thing is in the future, we're planning also doing co-simulation, doing a system simulation between aircrafts and also with aerodynamic CFD. So we can do a co-simulation between those. So if you guys want to know more about us, just please visit stasoftware.com. If you have any questions or discussion you want to have, you can contact us through the support@stasoftware.com. And this is the QR code on the right-hand side. You can follow us on LinkedIn to get the latest update on any future webinars. And this concludes my presentation. If you guys have any questions, feel free to ask. I'm more than happy to answer some of the questions. So I see there's a question here. So we have a person asking why we chose couple flow and sub-segregated flow solver since the analysis is subsonic. So the reason is, so for this particular case, we actually went in and checked for, is there a difference whether we use couple flow solver or segregated flow solver? The answer is that it was less than like 0.01% changes. And realistically speaking, you could do a low Mach preconditioning for couple solver, so it can solve like low subsonic flows. And technically, we also expand this not just to very low subsonic. Like you have low subsonic, but you also have the range to where you like getting close to the compressor, like being compressible. So that's why we choose a couple solver, so we can have the capability of simulating that range of where it's kind of low subsonic, but also like getting to the 0.3 compressibility range. That is the reason why. And frankly, this whole like validation is actually building up for future webinar, actually like transonic. So likely we can build on top of what the process, the practices, and then we can better transfer and like translate into the transonic and supersonic, and so it can just spans kind of wider and later in the future as well. But yes, you could use segregated flow for low subsonic, but in our testing and our what we see, the difference is minimal, and we can keep a more consistent process, a CFD process and practices. That's why we keep it in a couple flow solver. So there's a second question is, can this CFD be used to assess aerodynamic forces on pods, radome, that are attached to wing and fuselage? So it really depends on the geometry. So if you have a streamline or I guess aerodynamic shape of a pod or radome, then yes, most likely yes. But you have a pure bluff body, like you have a purely spherical object instead of something like a teardrop shape, then the story changes. After that, the story does change. Bluff body aerodynamic is one of the hardest thing to simulate right now, just because of by nature how much vortex are shedding off a bluff body. But yes, it really depends on geometry. But if it's something that is in the capability of the turbulence model, right? Some turbulence models are more they're designed and they're tuned based on of what they simulate, right? So, but yes, it really depends, but it could.
Okay, so after today's presentation, we are going to be posting this video. Oh, you picked. Okay, we have more questions.
Yeah. So okay, let's answer. Ted, do you want to answer this last question before maybe ending?
Yeah, so the question is, you picked a specific solver model to run the simulation and referenced it because it works best. How many solver models are available in your solution, and how you narrowed it down to a specific one? It usually involves physical testing, in my experience. Yes, I mean, I think is the short answer to your question. Many models are available, like many SST, K omega, K epsilon, LES models are available. This was a steady state analysis. We did not do transient analysis. Many different models and solvers are available. I mean, for transient, even the simple C algorithm is available. So that was part of the analysis of the sensitivity studies. And yeah, in this case, we did have the physical measurements before running the CFD case. And our overall methodology is rooted in building the motivation of our approach. For example, we started with a 2D analysis, and 2D airfoil analysis experimental data is widely available across many different Reynolds number ranges and airfoil types, especially through the UIUC database. And so a lot of our methodology development was developed on the 2D airfoil, and then we implemented it for the 3D case. And so our methods development is where we are running many different cases, is on a simpler geometry under the same flow condition. And then we just transition that for the 3D case. So our overall CFD approach, we always try to find simple cases that are relevant to the production case, where we can validate our methodologies so that we can build the confidence. And then we transition those methodologies to a more complex case that requires more computational resources, that's more expensive to run, so that we can build our confidence. And we apply this approach to every case. And if there's physical measurements, then we try and validate and benchmark our case first. But if not, we try to find something similar or use the recommended best practices for that case.
Yeah, yes, Ted. I think you have a really good answer. Just so basically, we have like a logical process to use, like what Ted's talking about. We use a more root case, like for example, like in this case with 2D airfoil, and we assess the uncertainties in different models. But we're also not just looking at uncertainty, what they actually introduce to the end result, like the forces, but we also try to understand what physical is introducing. Like for example, SA versus SST K omega. Well, SA is quite like known that it separates early, and SST will separate a little bit later. So like we do try to understand the physical impact of each models, and or how transition model actually triggers a turbulence boundary layer kick in, when does it kick in, when you're transitioning, and those sort of like physical phenomena as well, not just uncertainty. But yes, this is kind of how we narrow it down to a specific one. And we do go back and have check cases, see if it's still valid, right? So like even though in the 2D case, we see this a pattern, and then we implement this pattern into 3D, but we still have like probe cases to make sure that it's still congruent to our understanding and how this will translate into the 3D case or a more complex case.
Okay, so like I was saying before, we will be posting the video. You guys have our contact information. We're happy to talk. Okay, so now I'm going to end the event, and we look forward to seeing you next time. Thank you, everyone.
Thank you, guys.